In 1954, workers clearing sand next to the Great Pyramid found something impossible. A boat, buried in pieces, sealed in a pit for over 4,500 years. When they finally put it back together, it wasn't some crude raft. It was a 43-meter ship, built with a level of precision that modern shipbuilders still study today. The wood wasn't even native to Egypt. It was cedar, hauled from Lebanon, across hundreds of kilometers of desert and sea. And that's the moment you have to ask yourself, if a boat buried next to the pyramid is this advanced, what does that tell you about the pyramid itself? Because here's the thing nobody tells you in school. We're not actually confused about how the pyramids were built. Archaeologists have found the ramps. They've found the workers' town. They found the payroll records written by the actual foreman in their own handwriting 4,500 years ago. The real story isn't a mystery. It's an engineering feat so absurd, so tightly organized, that it makes some of our modern megaprojects look sloppy by comparison. By the end of this video, you're going to understand exactly how roughly 20,000 people moved 2.3 million blocks of stone, some weighing as much as a school bus, into a shape so precise that its base is level to within just a couple of centimeters across 230 meters. Let's start where the Egyptians started, not with the stone, but with the ground. Before a single block was laid, the builders had a problem most people never think about. How do you make sure a structure this size doesn't end up crooked? The Giza Plateau is solid limestone bedrock, which is exactly why it was chosen. It's stable, it doesn't shift, and it can bear enormous weight without settling unevenly over centuries. But bedrock isn't flat, so the first job was leveling. The leading theory, supported by tool marks and construction remnants found on site, is that workers cut a grid of shallow trenches into the rock and flooded them with water. Water finds its own level, that's just physics. So by measuring the depth of water against the rock's high points, workers could calculate exactly how much stone to shave off to create a level foundation. It sounds almost too simple, but the result speaks for itself. The base of the Great Pyramid is level across its entire 230-meter footprint, with a margin of error of about 2.1 centimeters. To put that in perspective, that's a tighter tolerance than many modern parking lots. They also had to solve orientation. The four sides of the pyramid align with true north, south, east, and west with an accuracy of within 1/10 of a degree. The most credible theory is that they track the rising and setting points of specific stars, bisecting the angle between them to find true north, a method that doesn't rely on magnetism, which is good, because compasses didn't exist yet. So before construction even began, Egyptian surveyors had already achieved something most ancient civilizations never touched: a perfectly level, perfectly oriented building platform, carved directly into bedrock. Now came the hard part: getting the stone. The Great Pyramid contains an estimated 2.3 million blocks, with a combined weight somewhere around 5.9 million tons. Most of that stone, the core material, didn't have to travel far. It came from a quarry right there on the Giza Plateau, just a few hundred meters south of the construction site. You can still visit that quarry today. It's a massive depression in the ground, basically the missing piece of the puzzle, sitting right next to the finished picture. Quarrying limestone in 2500 BCE didn't involve explosives or steel. It involved something far more patient. Workers would first outline a block using copper chisels, cutting a groove around its shape. Then, they'd drive wooden wedges into the groove and soak them with water. As the wood absorbed the water, it expanded, and that expansion generated enough pressure to crack the stone cleanly along the line. It's the same basic principle some quarries still use with mechanical wedges today. Copper is a soft metal, which surprises people. How does soft metal cut through stone? The answer is abrasion. Workers used copper saws and drills in combination with wet sand, which is extremely hard. The copper tool wasn't actually the cutting agent. It was a carrier, dragging quartz sand back and forth across the stone until it wore a groove. Slow, repetitive, but completely effective at scale. For the core blocks, this process was almost industrial. Teams worked in parallel across the quarry face, extracting block after block in a rhythm that could plausibly deliver hundreds of stones a day at peak construction. But the core blocks were the easy part. The pyramid also needed Granite for the internal burial chamber and stress-relieving structures, quarried from Aswan, about 800 kilometers south. Fine white limestone for the outer casing. The polished shell that once made the pyramid gleam in the sun, quarried from Tura, across the Nile. Some of those granite blocks weighed over 50 tons. And they had to travel hundreds of kilometers before a single person could even think about lifting them into place. Which brings us to the part that genuinely impresses engineers today: transportation. Here's a fact that used to baffle historians and now, thanks to a 2014 discovery, doesn't baffle anyone anymore. For decades, one theory dominated: that Egyptians dragged stone blocks across the desert on sledges, and that dry sand created so much friction the whole process should have been nearly impossible. Then, a team of physicists actually tested it. They discovered that when you wet the sand in front of a sledge, just enough to create surface tension between the grains, friction drops dramatically. Wet the sand correctly, and the pulling force required can be cut roughly in half. And here's the kicker. Egyptian tomb paintings from this exact era show workers doing precisely that. A person standing at the front of a sledge, pouring water onto the sand just ahead of the runners. For a long time, people assumed that was ceremonial or symbolic. Turns out it was just good engineering. So picture the scene. Teams of men, sometimes dozens per sledge for the largest blocks, hauling limestone across specially prepared, dampened tracks from the quarry to the construction site. But dragging blocks a few hundred meters from the local quarry is one thing. Moving 50-ton granite blocks 800 kilometers from Aswan is a completely different problem. And the answer to that problem is the Nile. The Nile wasn't just a water source for Egypt, it was the highway system. During the annual flood season, when the river rose and expanded closer to the plateau, massive barges could carry stone blocks almost directly to the construction site. Canals and harbor basins near Giza, confirmed by archaeological excavation, allowed boats to dock within a short distance of the pyramid itself. This is actually where our earlier story about the buried boat becomes relevant again. That level of shipbuilding sophistication wasn't a coincidence. Egypt's ability to build the pyramids was inseparable from its ability to move massive cargo by water. Without the Nile, there is no Great Pyramid, full stop. Once the stone arrived at the site, though, there was still one enormous problem left. How do you lift a 2.5-ton block, or in some cases a 50-ton one, up to a height of 146 meters? This is the part people love to argue about, and honestly, it's the most fascinating engineering question in the whole build. We know ramps were used. We have physical remains of construction ramps at multiple pyramid sites, including one at the unfinished Pyramid of Sekemket and clear ramp remnants around Giza itself. The debate isn't whether ramps were used, it's which kind, and how they evolved as the structure got taller. Theory 1. The straight ramp, the simplest idea. One long ramp running straight up one face of the pyramid. The problem is math. To keep a ramp slope gentle enough for men to drag multi-ton loads, a ramp reaching the pyramid's full height would need to be over a kilometer long and would require more material than the pyramid itself. That doesn't add up. This theory is mostly ruled out for the pyramid's upper sections, though it may have been used for the lowest courses. Theory 2. The spiral ramp. This theory proposes a ramp wrapping around the exterior of the pyramid as it rose, using the pyramid's own faces as a support structure, similar to a spiral staircase. It solves the length problem elegantly. The issue: a ramp like this would obscure the corners, making it nearly impossible for surveyors to continuously check the accuracy of the pyramid's angles as it rose. Given how precise the final structure is, most researchers think there had to be a way to keep verifying the geometry throughout construction, something a fully wrapped spiral ramp would prevent. Theory 3. The internal/zigzag ramp. This is the theory that's gained the most traction in recent years, especially after research published by French architect Jean-Pierre Houdin and, separately, findings from a French-Egyptian team led by Bob Breyer. Using microgravimetry, a technique that measures subtle density differences inside the structure to detect hidden voids and passages. Their scans revealed what appears to be a spiral-shaped internal structure just beneath the pyramid's surface. The idea: an external ramp handled the lower third of the pyramid, where the vast majority of the material sits. Then, for the upper two-thirds, where the volume of stone needed drops off dramatically, builders switched to an internal ramp, spiraling up just inside the outer casing, using the pyramid's own mass as the ramp's structural support. This would explain both the precision, corners stayed visible for most of the build, and the sheer efficiency of the process, less wasted ramp material as the structure narrowed toward the top. Theory 4. Levers. In 2018, an Egyptologist named Mark Leiner, one of the foremost living experts on Giza, proposed a hybrid idea after studying where patterns and construction debris. Ramps got material to a certain level, and simple wooden levers finished the job, walking blocks upward using the same rocking lever technique that's still used informally by builders in parts of rural Egypt today. The honest answer, if you want the honest answer, it was probably a combination. Straight or fanned ramps for the base, some form of internal or wraparound ramp system for the middle and upper sections, and manual leverage for fine positioning. This wasn't one clever trick. It was a layered system of solutions, evolving as the challenge changed with height. And none of this works without one more thing: people. Tens of thousands of them organized, fed, housed, and paid. This is where the story gets even more remarkable. For over a century, popular culture insisted the pyramids were built by slaves. Whips, chains, forced labor under a tyrant king. It's a compelling story. It's also almost certainly wrong. The turning point in this debate came from actual archaeology, not speculation. In the 1990s, archaeologists Mark Leiner and Zahi Hawass excavated a site just south of the pyramids, now known as the Lost City of the Pyramid Builders. What they found was a purpose-built town, bakeries capable of producing thousands of loaves of bread daily, breweries, massive food storage facilities, and, critically, cemeteries. The cemeteries told the real story. Workers buried near the pyramids were interred with tools of their trade and, in some cases, honorary titles. Some tombs even bear inscriptions with worker pride, referencing their teams by name: Friends of Khufu, Drunkards of Menkaure. These aren't the burials of anonymous slaves. These are the burials of paid laborers who were proud of the work they did. Then, in 2013, came a discovery that essentially closed the debate for good: the Diary of Mirror. Mirror was a mid-level official who led a team of about 40 men transporting Tura limestone by boat to Giza. His papyrus logbook, the oldest inscribed papyrus ever discovered, records his crew's daily activities in specific mundane detail: which days they worked, which days they rested, what they transported, and when they got paid. It reads like a modern work timesheet. That's not the record-keeping style you'd expect from a system of forced, unpaid slave labor. It's the record-keeping style of an organized, waged labor operation. So, who were these people? The evidence points to a rotating labor system. Farmers, during the months when the Nile flooded their fields and agricultural work was impossible anyway, were conscripted into labor crews, likely as a form of tax obligation, similar to how some ancient societies required citizens to contribute either goods or labor to the state. In exchange, they received housing, and a diet that has been reconstructed from bone analysis and food storage remains to include substantial amounts of bread, beer, and meat, beef, and mutton, which in ancient Egypt was actually a fairly high-quality diet, arguably better than what an average farmer ate at home. Estimates for the total workforce vary, but the most credible modern estimates, based on the settlement's food production capacity and housing footprint, land around 20,000 to 30,000 workers at any given time, not the hundreds of thousands ancient Greek historian Herodotus claimed centuries later. Herodotus, writing roughly 2,000 years after the pyramids were built, is generally considered an unreliable source on construction details. He was working from second-hand stories, not eyewitness accounts. These workers were organized into gangs, and those gangs were split into smaller units of around 20 men, each with its own identity and internal competition, not unlike a modern construction crew with team names painted on their hard hats. This mattered enormously for logistics. You don't organize 20,000 individuals. You organize 1,000 units of 20, each with a foreman reporting up a clear chain of command. It's the same basic principle every large modern organization still uses today. Feeding this workforce alone was a massive operation. Cattle bones found at the site suggest something like 21 cattle and 23 sheep were slaughtered daily just to feed the workers. An enormous logistical undertaking layered on top of the already enormous logistical undertaking of building a mountain of stone. With material, transport, and labor solved, the last challenge was accuracy. Because a pyramid isn't just a pile of stone. It's a very specific geometric shape, and getting that shape wrong even slightly compounds catastrophically as the structure rises. Internally, the Great Pyramid isn't solid. It contains the King's Chamber, the Queen's Chamber, the Grand Gallery, and a series of narrow shafts whose exact purpose is still debated. Some researchers believe they were symbolic pathways for the pharaoh's soul, aligned with specific stars, though this remains a topic of genuine scholarly disagreement rather than settled fact. Above the King's Chamber sit 5 relieving chambers, stacked granite slabs designed specifically to redirect the crushing weight of the stone above, so it doesn't collapse the ceiling below. This is a stress engineering solution that wouldn't look out of place in a modern structural design textbook. And it's a strong signal that the builders understood load distribution, not just brute force stacking. The outer surface, when finished, wasn't the stepped, exposed block structure we see today. It was covered in polished white Tyrol limestone casing stones, cut so precisely that the seams between them were reportedly less than a millimeter wide in places. Most of that casing was stripped away over the following centuries, much of it repurposed to build medieval Cairo, which is why the pyramid today looks rougher than it did in 2500 BCE. When it was complete, it would have gleamed almost white in the desert sun, visible from a significant distance. And all of this, the leveling, the quarrying, the transport, the ramps, the labor organization, the internal engineering, is generally believed to have been completed in roughly 20 years, within the reign of Pharaoh Khufu. Some estimates suggest this pace implies installing a new block, on average, every few minutes of the working day, for 2 decades straight, without modern machinery. 2330, 26:30, Chapter 7. Why the alien theory doesn't hold up. It's worth addressing directly, because it comes up constantly in the comments of any pyramid video. The idea that this was too advanced for ancient humans, and must have involved some kind of outside help. The honest response isn't offense, it's evidence. We don't have to guess how the pyramids were built, because we have the receipts. Literally. We have mirrors, papyrus timesheets. We have the workers' town with its bakeries and cemeteries. We have the quarry marks showing exactly how blocks were cut. We have ramp remnants. We have unfinished pyramids, like the one at Mitam, which partially collapsed, that show us construction techniques mid-process, essentially frozen in time as a mistake. We also have a very clear developmental record. The Great Pyramid didn't appear out of nowhere. It's the culmination of a design process that includes earlier, less refined pyramids, the Step Pyramid of Djoser, the Bent Pyramid, the Red Pyramid, each one testing and correcting engineering mistakes from the one before it. The Bent Pyramid, in particular, appears to change angle partway up because builders realized mid-construction that their original angle was structurally unstable and adjusted. That's not the record of a civilization that received a finished blueprint from an outside intelligence. That's the record of a civilization learning, failing, and improving. The same process every engineering tradition in human history has gone through. The truth is genuinely more impressive than the myth. What the Egyptians achieved wasn't a shortcut. It was decades of accumulated skill, applied by tens of thousands of organized, paid, fed, and evidently proud workers, using tools that seem primitive by our standards but were deployed with a level of precision and planning that any modern project manager would respect. So the next time someone tells you the pyramids are unexplainable, you'll know that's not really true. What's unexplainable is why we ever stop being impressed by what humans can actually do without any shortcuts at all. If you found this as fascinating as I did putting it together, there's a companion mystery I haven't touched on yet. What's actually inside those unexplored shafts detected by muon scanning in 2017, and why researchers still haven't been able to reach them. That's coming in a future video, so make sure you're subscribed so you don't miss it. Let me know in the comments, which theory do you find most convincing? The internal spiral ramp or the combination approach? I read every one of them. See you in the next video.